Hello everyone, this is the spotlight video for our paper, an opportunistic linear convex algorithm for localization in mobile robot networks. In this work, we consider a network of mobile robots with arbitrary motion in the presence of at least one node with known location, which is referred to as an anchor or a beacon. We provide a distributed algorithm to find the locations of robots using only local communications. This algorithm is opportunistic in a sense that a robot only performs a location update when it finds some nearby robots, and the updates are based on a triangle inclusion test that only requires local distance information. We show that the proposed algorithm requires only one anchor to localize an arbitrary number of mobile robots. Let's take a look at different update scenarios by a simple example in R2. Consider a network of 10 mobile robots and one anchor, and let's focus on the robot in blue color. At the beginning, the robot does not find any neighbors and therefore does not perform any update. It moves in the region until it finds 3 other robots within its communication radius. However, the robot does not lie inside the convex hull of these 3 neighbors, which is a triangle in R2. So again, the robot does not perform any update and continues to move in the region. Later, the robot finds 3 neighbors and it does lie inside their convex hull. In this case, the robot updates its location estimate as a linear combination of the location estimates of its neighbors and continues to move. Finally, we see a different update scenario where the robot finds more than 3 neighbors and it lies inside 2 different sets of convex hulls. In this case, it randomly chooses a set of neighbors and performs an update. The main difference in this case is that an anchor is involved in an update and it provides a reliable location information for the updating robots, and it improves the location estimates of this robot. Here are the simulation results for networks with 5, 10, 20, and 100 robots and only one anchor in R2. We use the second norm of the error vector to characterize convergence, and we take the average over 20 different simulations. We can see that in the absence of noise, the error eventually goes to 0 and the robot's location converges to the exact true locations. In practice, all measurements are noisy, and we will have noise on the motion as well as the distances to the nearby nodes. And these are 2 parameters that are crucial in the implementation of our algorithm. As you can see in the simulation results for a network with 1 anchor and 100 robots, when we add 10% noise on distance measurements and 1% on the motion at each iteration, the error soon gets larger than the dimension of the region, and it keeps growing if we use the original algorithm. Therefore, we suggest a few modifications to the algorithm to counter the undesirable effects of noise. And as you can see in the figure on the right, after we apply the modifications, the error gets bounded by the communication radius of the robots. Thank you for your attention, and we look forward to seeing you at the conference.